This video is presented to you by www.testprepadda.com. Dear students, in this video lecture I will talk about the acidic strength of benzoic acid and substituted benzoic acids. First of all, what is benzoic acid? This is benzene ring. When COOH group, carboxylic group, is directly attached with benzene ring, this is known as benzoic acid. This benzoic acid is acidic in nature because it can release H plus and giving carboxylate ion. So this is a protonic acid. It releases a proton. So that is why this carboxylate ion will be called as conjugate base of this benzoic acid. Since we are saying this benzoic acid as acidic, its conjugate base must be stable. So we will check the stability of this carboxylate ion. The conjugate acid base theory says if the conjugate base is stable, its parent will be acidic in nature. So here what is happening? Let me write the resonating structures here. So it is like this. Now you can see double, single, double bond in conjugation with double bond. That is why here also you can write the resonating structure. So the shifting will be like this, and that is why the resonating structure will be written like this. The positive will be generated at this carbon. Now another resonating structure will be written like this. Plus will come here, double bond here, one double is already here. Now next resonating structure can be written here. Double bond shifting like this. Positive will come here. O minus, O minus. Now the next resonating structure will be like this. So these are the different resonating structures of carboxylate ion. Since carboxylate ion is resonance stabilized, we say that its parent benzoic acid is acidic in nature. Okay, but the question arises, benzoic acid itself resonance stabilized. If benzoic acid itself resonance stabilized, this process should move in the backward direction. Let me write the resonating structures of this benzoic acid first. First lone pair in conjugation with double bond. So I will write the resonating structure in this manner. Minus here, double O will get plus. Now next resonating structure I can write. Now double, single, double bond in conjugation. That is why resonance. So this bond will be broken. The electron will shift in this manner. And that is why resonating structure. Plus will be generated here. Double bond here. Minus is already here. Now OH. Next resonating structure I can easily write here. Electrons will shift in this manner. Plus will come here. Double CO minus OH. Next resonating structure I can write, plus will come here, double O minus OH, and then this resonating structure. Okay, so these are the different resonating structures of benzoic acid. The problem is both parent acid benzoic acid as well as conjugate base carboxylate ion, both are resonance stabilized. So how will we decide whether this process will move in the forward direction or it will move in the backward direction? So just check the resonating structures, the resonating structures. In case of benzoic acid, you will find resonating structures where oxygen gets positive charge. Oxygen is electronegative element. Electronegative element is capable of holding negative charge. But electronegative element, when gets positive charge, it will destabilize the original molecule. It will destabilize the actual molecule. While in case of carboxylate ion, you will not find positive charge on oxygen. That is why we say carboxylate ion is more resonance stabilized than the benzoic acid. That is why this process is more in the forward direction, and relatively benzoic acid is acidic. My point is clear? So this way we explain the acidic character of benzoic acid. Acidic character of benzoic acid is explained by the resonance stabilization of carboxylate ion, benzene carboxylate ion. My point is clear. Now I will compare the benzoic acid with aliphatic acid. If I write the benzoic acid, it is this. If I write the aliphatic acid, it is this. Okay. Now, this C6H5, this C6H5 is actually minus IFA group, minus IFA group. So, in if I talk about this benzoic acid, here it is electron withdrawing. Here it is electron withdrawing this way, minus IFA. But because of the COH, there will be R effect, and R effect gets preference over inductive effect. Mesomeric effect gets preference over inductive effect. So overall, it is electron releasing. Overall, it is electron releasing. But in case of aliphatic carboxylic acid, it is only electron releasing group R. So it will push the electrons towards COH. So this is pure electron releasing group. That is why when you compare benzoic acid with aliphatic acid, aliphatic acid, if I take the example CH3COH, acetic acid. So benzoic acid will be more acidic than CH3COH. But if I compare this benzoic acid with formic acid, H is attached. So H is what? Neither electron withdrawing nor electron releasing. In both the cases, overall it is electron releasing. But here neither electron releasing nor electron withdrawing. That is why this will be more acidic than benzoic acid. So benzoic acid is more acidic than other aliphatic acids other than formic. My point is clear. And this can be explained with the help of Ka values also. If I write the Ka values of these acids, the acetic acid Ka value is 1.8 into 10 raised to minus 5. For formic acid, the Ka value is 1.7 into 10 raised to minus 4. And if I write for benzoic acid, it is 6.4 into 10 raised to minus 5. Clearly, you can see formic acid is more acidic than benzoic acid, more acidic than acetic acid. My point is clear. Dear students, now I will tell you about the effect of substituents on benzoic acid acidic strength. Okay, first I will take nitrobenzoic acid. Let me write, this is the benzoic acid. If I write different nitro substituents, I can write NO2 at para. I can write NO2 at meta. I can write NO2 at ortho. Let me tell you about NO2 group first. NO2 is what? Minus M effect group. Minus M effect means electron withdrawing group through what? Resonance. Second, it is also minus I effect group. Minus I effect means it is electron withdrawing group. Again here we will say inductive effect. So both inductive effect and mesomeric effect, both are supporting each other. Overall it is electron withdrawing group. So here electron withdrawing group, here electron withdrawing group, here electron withdrawing group. Here you will not find any electron withdrawing. So electron withdrawing group will increase the acidic strength of this carboxylic acid, because the will electron withdrawing group will decrease the basic strength of the conjugate base. If the basic strength of conjugate base decreases, the acidic strength of parent increases according to conjugate acid base theory. That is why the last will be what? The last will be benzoic acid. The last will be benzoic acid. And then if I compare these three nitro, here you can see minus M minus I, minus M minus I. Sorry, here minus M will not work because NO2 is at meta position. Here minus M minus I. So if I compare these three, obviously when NO2 is at meta position, here only I effect is working. That is why the electron withdrawing effect will be less, and that is why here we will write meta isomer. And out of these two, para-nitro and ortho-nitro will withdraw electrons more because inductive effect is distance dependent. Distance dependent, that is why here the electron withdrawing effect will be more. Electron withdrawing effect more means more acidic. That is why ortho greater than para greater than meta greater than benzoic acid. This is the correct order. My point is clear. So this is about the electron withdrawing group. Now I'll talk about the electron releasing substituent. Now the methoxybenzoic acid. So if I write, first I'll write normal benzoic acid, then I'll write substituted benzoic acid. If I write OCH3 at para, then OCH3 at meta, and then OCH3 at ortho position. Let me tell you about CH3O group. CH3O is what? Because of the lone pair, it is plus M effect group. Plus M means electron releasing group through what? Resonance. Through resonance. And at the same time, it is minus I effect group, means electron withdrawing through inductive effect. But Mesomeric effect gets preference over inductive effect. That is why overall it will be electron releasing group. Overall it will be electron releasing, and the acidic strength of these carboxylic acids will be decided by the combined effect of the two. Here you can see we have plus m, minus I both, and minus I will be maximum here. Here we have only minus I, electron withdrawing effect. Here we have plus m and minus I, but minus I effect is minimum. Okay, here we do not have any plus m or minus I of the substituent. So, if you compare out of these four, only in case of meta you are finding net electron withdrawing effect. So, this should be the most acidic among all methoxy. So, we should get order as this meta isomer should be more acidic. While in this para methoxy and orthomethoxy, overall it is electron releasing, and that is why they should be less acidic than the benzoic. So now it should come benzoic acid, and out of these two, inductive effect is more in case of ortho. That is why this should be more acidic than the para group. So it should be ortho greater than para. This should be the order. This should be the order. But experimental data says that this order is not correct. The correct order as per the K values is ortho isomer greater than meta isomer greater than benzoic acid greater than para isomer. This is the correct order. Here you can see ortho was here, but now the ortho becomes number 1. Now why? To explain this abnormal behavior, we say that when OCH3 group is present at the ortho position of COH, because of this steric effect, COOH loses the planarity with the ring, and because of which its acidic strength increases sharply, and this is called as ortho effect. Just read these lines. Ortho effect. When a group is attached at ortho position of benzoic acid, it causes slight non-planarity between COH and ring. This decreases the minus R effect of COH and CO minus groups. As a result, acidic strength of benzoic acid increases because minus R effect has the effect of decreasing the acidic strength of benzoic acid. This effect is known as ortho effect. I'll take one more example here to explain this ortho effect. This is very, very special. For example, if I take methyl benzoic acid, let me write, this is normal benzoic acid, this is para-methyl benzoic acid, this is meta-methyl benzoic acid, this is ortho-methyl benzoic acid. Okay, now first of all, what is this CH3 group? CH3 is plus I effect group and plus R effect group. Okay, so overall it is electron releasing group. Overall it is electron releasing. Everywhere electron releasing. Here both plus R and plus I will work. Here only plus I will work. Here both plus I and plus R will work. Here no electron releasing group. So this should be the most acidic most acidic among all possible compounds here. So the expected answer, expected is what? Benzoic acid greater than. Now what will you write? You will write meta, because here the electron releasing effect is minimum. So answer should be meta isomer. And then out of these two, in which case electron releasing group is more? Here the effect is more, because here the inductive effect as well as R both are working, and inductive effect will be maximum at ortho, and here the inductive effect is minimum. That is why now the its answer should be para, and then it should be ortho. But experimentally we have found that this answer is wrong, and you will be surprised to know that ortho, although we have got minimum, but actually this ortho is maximum. So ortho isomer is most acidic here, then benzoic acid, then meta isomer, and then para isomer. And this is explained with the help of this ortho effect. Now, how we say that methyl group, a bulky group, is attached at ortho position. Because of this, this COH loses its plenarity with the benzene ring. So its minus R effect that COH provides, that decreases, and due to which its acidic strength increases. And students, let me tell you, nearly all ortho substituted benzoic acids are stronger than the, let me tell you, benzoic acid. Now I am giving you the list of benzoic acids with acidic strength order on the basis of pKa values. pKa less implies more acidic benzoic acid. This is the list of important benzoic acids with pKa values, and let me tell you, less pKa implies more acidic. So this is the order. You can see orthonitrobenzoic acid is most acidic here, and after parachlorobenzoic acid we have parabromobenzoic acid, and this way you can see different substituted benzoic acids. So here you can see ortho position NH2 is attached. This is the least acidic here among given acids. And if you look at this orthohydroxybenzoic acid, this OH group is not very bulky. OH is not very bulky, so here it is difficult to explain this high acidic strength on the basis of ortho effect. So for high acidic strength of this orthohydroxybenzoic acid, we give another explanation. If I write the carboxylate ion here, carboxylate ion and OH, we say that because of intramolecular hydrogen bonding, this carboxylate ion is stabilized. Extra stabilization of this carboxylate ion, benzene carboxylate ion, because of intramolecular hydrogen bonding, and as a result the parent acid, that is orthohydroxybenzoic acid, its acidic strength increases. Similar kind of explanation can be given for this high acidic strength of orthonitrophenol. Here if I write the conjugate base, that is this nitro, I can write as this. You can see minus plus, this interaction, because of this carboxylate ion, benzene carboxylate ion, becomes extra stable, and extra stabilization of this conjugate base implies more acidic strength of this orthonitrobenzoic acid. Now how will you explain the acidic character of these two? Means halo benzoic acid, whether it is chloro or bromo. So here if I say Cl or Br, this halogen group is a bulky group here. This bulky group, because of this COH loses its planarity with the benzene ring. As a result, its minus R effect decreases, which is responsible to decrease the acidic strength. And that is why, because of ortho effect, we explain that acidic strength of these two compounds. Are you getting my point? So this way, we explain the high acidic strength of orthonitrobenzoic acid, orthobromobenzoic acid, orthochlorobenzoic acid, orthohydroxybenzoic acid. Okay, now after going through this list of benzoic acids, you can easily say, except this orthoaminobenzoic acid. Except this, all other ortho-substituted benzoic acids are stronger acid than this benzoic acid. My point is clear. Okay. So this is all about the acidic strength of benzoic acid and substituted benzoic acids. Dear students, in the next video lecture, I will talk about the basic strength of aniline and substituted anilines. Thank you. This video is presented to you by www.testprepadda.com. TestPrepAdda.com provides free audio-visual lectures of different subjects by expert faculties, free online tests prepared by expert faculties to students who are preparing for engineering or medical entrance exams or planning to take exams like KVPY, Olympiad, etc. It provides a platform where students can interact with mentors to improve their performance in the exams. The mission of this online medium is to help students to achieve their goals. Log on to www.testprepadda.com to watch free video lectures on different topics, to download free revision notes, to take free chapter-wise online tests, progressive test, and mock test, to discuss doubts with mentors. Thank you for watching the video. To stay up to date with the latest videos, subscribe to our YouTube channel. Like us on our Facebook page, Test Prep Adda. All the best.